Hello and welcome. This is Cambridge O-Level Chemistry Paper 4, alternate to practical. The subject code is 5070. This is May-June 2023 exam, and this is version 1 of this exam. So before we start, I will request you that if you have not subscribed to this channel, please subscribe and you will be getting all the latest updates as well as the uploads of the solutions I will be posting. So let's start. First question, it says, a student uses chromatography to separate the dyes in a food coloring. Figure 1.1 shows the apparatus the student uses. Name the apparatus X. So let's see what we have here. So we have a beaker that is closed with a lid. We have a chromatography paper inside it. There is a solvent, and that solvent, and since the paper is immersed in the solvent, the fluid or the solvent is rising up into the chromatography paper, and the dyes are separated inside this chromatography paper, and the spots are visible for us. So name the apparatus X. So the apparatus X is actually a beaker. This is a beaker. Then part B, state why it is important to have a lid on X. So the lid of X, basically prevents this solvent from evaporating, and it also keeps, you can say, if this solvent is evaporating, so it also keeps the saturated vapor of that solvent within this beaker. So that's the reason. So it prevents the solvent from escaping and keeps these entrapped air saturated with the vapor of the solvent. So because the evaporation is taking place at all temperatures, there will be some sort of evaporation of the vapor of the solvent, and that basically is entrapped, or whatever the vapors will be there, that those vapors will be entrapped inside this beaker. So moving ahead, part C, it says state why the straight line is. Number one, above the level of the solvent. Number part two, drawn with a pencil. So why this is above the level of the solvent? So this is to ensure the separated. So the separated dye does not dissolve in the solvent. Okay, so the thing is, say for example, this is our beaker. This is our fluid solvent level. This is the, say for example, the paper, and this will be our line. So if this line is inside this solvent, what will happen is that whatever the dye is there on this line, this dye will dissolve in this solvent and mix inside. But what happens here is that the solvent rises up because of the reaction into the chromatography paper, reacts with it or dissolves with it, and takes the dye with it, and rises up. And the constituent colors or the components separates themselves based on their mass as they rise up in because of the capillary reaction. So then why this line is drawn with a pencil? So pencil is basically insoluble. Pencil is insoluble in the solvent and does not react with the dye. Okay, that's why it's drawn with a pencil. Then it says, what is the RF value of one of the dyes in the food coloring is 0.6. In the separation, the dye travels 5.7 centimeters. Calculate the distance traveled by the solvent during the separation. So basically, remember what is RF value? So RF value, for example, this is your chromatography paper. This is your initial line, and this is your distance travel. Say, let's call it as Y. And this is your, it's called solvent front. Right? This is your initial line, or you can call it as baseline. Okay. So RF value, say for example, this is your dye one. Say, let's call it as X. So the RF value for X will be, so let's call it A. For constituent A will be X divided by Y. Okay. So this will be your RF value, or RF value for X, or it is the this is how it is calculated. So for this case, it says the RF value of one of the food dye. So one of the food dye, the value is given as 0.6. In the separation, this dye travels 5.7. So it means that the dye has traveled 5 point, means that X is equal to 5.7 centimeter. Calculate the distance traveled by the solvent during the separation. What is the solvent front? So we have to calculate Y. So simply just put these values in this above formula. So let's calculate. It would be 5.7 centimeters divided by solvent distance. And this is equal to 0.6. So solving it will become solvent distance. This is equal to 5.7 divided by 0.6. This is centimeter. And this comes out to be 9.5 centimeter. The answer will be 9.5. So remember, this is how you calculate this value. Next, part 2. It says, white vinegar is colorless solution containing ethanic acid. The student titrates 0.4 mole per decimeter cube aqueous sodium hydroxide with 2 samples of vinegar, vinegar A and vinegar B. The student does 4 titrations, 2 with A, 2 with B. So the student, step 1, it says, uses volumetric pipette to add 25 centimeter cube of 0.4 mole decimeter cube of sodium hydroxide to a conical flask. When sodium hydroxide is NaOH. So the concentration of this and volume of this is, concentration and volume. So remember, this is the concentration, this is the volume. Then part 2. Add 5 drops of indicator into the conical flask. Part 3. Add A from burette while swirling the contents of the flask, adding drop by drop near the end point until the solution changes color. Now, step 4. Student empties the conical flask and rinses it with distilled water. Step 5. Repeats steps 1 to 4. Step 6 repeats steps 1 to 5 using B instead of A. See? Then part A, it says figure 2.1 shows burette readings of 2 titrations with vinegar. So this is your titration 1, this is your titration 2. So the student has performed 2 titrations and there is certain volume of vinegar that has been utilized. Now record the readings, the burette readings in table 2.1, final value, initial value, and the volume used. So this is initial value, this is final value. For titration 1, initial value is 0, final value is 24.9. Here the initial value is 12.3. The final value is 37.4. Okay. So now let's record them. Okay. So the initial value, initial value one is 0.0. The second initial value is 12.6. Remember 12.3. Yes, 12.3. Okay. Oh, so not 6, 12.3. Then final value. So titration 1, titration 2. Yes. Then we have final readings 24.9. Here the value was 37.4. This is yes 37.4. So subtracting these values, initial minus final, total volume used will be V final minus volume initial is equal to V total. Okay, the volume of A used, or you can call it V used. Okay, then just subtract 37.4 minus 12.3. It comes out to be 25.1. So 25.1 centimeter cube will be the volume used. Then it says in figure 2.2, the burette readings for one of the titrations with vinegar is shown. So the first case 12.6, initial value is this. The volume used will be 12.5. Record the burette readings and calculate the volume reading. So we have done it earlier. So the other case is the final reading 25.123, 25.3, and the initial value is 12.6. So subtract them, value will be 12.7. Okay. Then part C, calculate the mean value of A and B to neutralize 25 centimeter cube of 0.4 mole decimeter cube of sodium hydroxide. So mean of A, remember, mean of A will be the average of both values. So 24.9 was 1, then 25.1 and divided by 2, the mean value comes out to be 25.0. So it will be 25.0. Then mean of B, the mean of B will be the values we calculated were 12.5 plus 12.7 divided by 2. It comes out to be 12.6 centimeter cube. Again, this was centimeter cube. So 12.6 centimeter cube. Okay. Then it says suggest why the titration A and B are repeated. So basically, we in such in these neutralization reaction or acid and base salt, acid and base titration reactions, we have to repeat these reactions or these processes so that we ensure repeatability, consistency of the results. So to ensure repeatability and consistency of the results. Okay. Then moving ahead, part D, it says the equation for the reaction between ethanic acid and sodium hydroxide is shown. The answer to B shows the mean value of B used to neutralize 25 centimeter cube or 4 mole decimeter cube of sodium hydroxide. Calculate the concentration of ethanic acid in B. So with vinegar B, volume is 12.6. So for B, volume of vinegar used is 12.6 centimeter cube. Okay. So from this equation, we can see that 1 mole of sodium hydroxide requires 1 mole of vinegar to perform reaction. So we can say that 1 mole of sodium oxide requires 1 mole of E. Okay. Uh, then, so that we have, how many moles we have here? So we have 0.4 mole per 1000 centimeter cube. So remember, 1 decimeter cube is equal to 1000 centimeter cube. So we calculate the number of moles used, multiply by 25 centimeter. This gives us 0.01 mole of sodium hydroxide, and that will require 0.01 mole of B. Okay, so we have to now calculate the concentration. So we need 0.01 mole of B. So what would be the concentration? So concentration will be 0.01 mole divided by the number of volume used. So 12.6 centimeter cube. So this will give me concentration in mole per centimeter cube. And now I have to multiply it, or sorry, further divided by, first calculate. So this comes out to 0.01 divided by 12.6. It comes out to be 7.936 mole per centimeter, and I have to multiply it by 1000 to get concentration in mole per decimeter cube. So simplifying it, it multiply by 1000. This was for 10 to the power minus 4. So this comes out to be 0.7936. So we'll approximate it as 0.794, or you can also call it 0.8 mole per dm cube. Okay, so 0.794, or you can write it there 0.8 mole per dm cube will be your required answer. Okay, so moving ahead, it says use your value in D to calculate the mass of ethonic acid in 500 centimeter cube of B. So concentration is equal to, let's call it 0.9794 moles per decimeter cube. This means 0.794 moles per 1000 centimeter cube. We have to find out now the moles of B in 500 centimeter cube. So these are 0.794 moles will be in 1000 centimeter cube. So just multiply by this whole number, multiply by 500. This will give you the value in moles. That comes out to be 1000. So it will be 0.363968 moles, or approximately you can call it 0.4 moles. Okay, so the mass will be number of moles multiplied by molecular mass, approximately 0.4 multiplied by 60. So this is equal to 24 grams. Or if you go with 0.3968 multiplied by 60, this value will be 23.8. So mass will be 23.808 grams, or you can call it as 24 grams. So anyway, this will be our answer. So then it says use the answers to B and E to calculate the mass of ethonic acid in 500 centimeter cube of A. So remember, for A, volume used. First of all, for A, volume used was, what was the volume used? So volume used was 25 centimeter cube. Okay, so 25 centimeter cube. So the concentration of A will be 0.4 mole per 1000 centimeter cube multiplied by 25 centimeter cube. So the concentration of A will be 1000 multiplied by 0.4 comes out to be 0.01 mole per 0.5. So this is the 0.0 moles concentration of A, or this is basically number of moles of A. A, so this much moles and this much moles are in 25 centimeters, that gives us the same. So the number of moles 0.01 mole. So then concentration of A will be 0.01 mole, and that will be present in 25 centimeter cube. So this will be equal to 0.01 divided by 25. So it will be 4 into 10 to power minus 4 moles per centimeter cube. So this will be the concentration. And now the question is, what are the number of moles of ethanic acid that are used? Oh, so just like what we have done. So we need 1 mole of sodium hydroxide will require 1 mole of this. So this much moles of sodium hydroxide will require. So we have number of moles. This is basically number of moles of NaOH. This is number of moles of NaOH. So 1 mole again NaOH gives 1 mole of A. So this much 0.01 mole of NaOH will give 0.01 mole of A. So the volume of A used, remember, is this. So this is mole of A, just like what we have done. So we have calculated number of moles. So from our moles, volume of this used was this. So this becomes our concentration. Okay. So concentration, this is the concentration of A. This is the concentration of A, or the vinegar that is used. So now we have found out the concentration. So this is the concentration which we have used earlier in this part. So we have this concentration now. So that is the moles of A used. Number of moles of A used in 500 centimeter cube. So we have concentration 10 power minus 4 moles per centimeter cube multiplied by 500 centimeter cube. So we multiplied the value with 500, it comes out to be 0.2 mole of A, or the vinegar used. The vinegar used is 0.2 moles. Let me change the color. So here what we see here that with B, or with ethnic acid B, or vinegar B, we are using this. So with vinegar A, we are using this many moles. So mass is equal to MR multiplied by number of moles. that is 0.2. Mass 60 multiplied by 0.2 comes out to be 12 grams. Okay, so the answer will be 12 grams. So this is how you will be solving this question. Okay, so moving ahead, it says, suggest why conical flask is rinsed with distilled water and not 0.4 mole per decimeter cube aqueous sodium hydroxide between titrations. So remember, distilled water removes any residue, whereas so DI or not, it's not deionized water, so you bounce it in. Distilled water removes the residues from the flask, also cleaning, or rather rinsing with, good word to write here is rinsing with NaOH will result in some NaOH remaining in the flask, thereby changing the volume of NaOH this results in more ethnic acid used, thereby our results will not be accurate enough. Then part H says some vinegars are brown rather than colorless. Suggest why this titration would not be suitable for finding the concentration of ethnic acid in brown vinegar. So remember, we are using an indicator to establish color change effect. So when we already have a brown vinegar, the color change will not be visible properly with this set of or with the indicators we are using. So that is the reason. So the color change will not be properly visible in brown vinegar. Okay, so when we're using a brown vinegar, the color change will not be visible properly. Okay, so that is how we go around this. Next part, question number 3. Again, remember, this is an important question. This is the A9 and cation detection problem. And at the end of your examination booklet, there will be a sheet that is given, and that basically shows you almost all the tests and what sort of precipitates are forming, and tests for gases, anions, and cations available for them. So if you see that sheet properly, you'll get to answer all these questions in no time. Okay, so let's start. It says question 3, a student investigates solution W and copper 2 carbonate. Okay, so we have two things. We have a solution W and copper 2 carbonate. Okay, the tests the students does on W are shown in table 3.1. Some of the observations for these tests are shown. So it says add aqueous sodium hydroxide. Okay, solution remains colorless. Okay, add dilute nitric acid and then aqueous barium nitrate to W. White precipitate is formed. Okay. And then it says add dilute hydrochloric acid, and then aqueous silver nitrate to W. Again, it says white precipitate. Plain test on W, no color was observed. Okay. So this is what we are getting, what is given to us. Remember, if you have the sheet in front of you, you will see that when you add aqueous sodium colorless solution, ammonium ion situation. Part 2, nitric acid, then barium nitrate. This is in white precipitate form. This is a test for sulfate. Ions add dilute hydrochloric acid and aqueous silver nitrate. This is a case where you go and check for, you can say bromine, maybe. So this is how it is. So let's say what it's asking. So the student uh, correctly concludes that ammonia is formed in test 1. Describe what else the student must have done to reach this conclusion. So number 1, what have done? So add a piece of aluminum and warm the mixture in the test tube. Use a damp red litmus paper to check the presence of a gas, and that gas is actually ammonia gas. So the litmus turns blue. Okay, so ammonia gas turns red litmus, damp red litmus paper blue. Okay, then part 2, it says state why the student cannot identify the anion from W from observation in test 3. So remember, the test 3 is dilute hydrochloric acid and aqueous silver nitrate. So HCl, so remember, adding dilute silver hydrochloric acid and barium nitrate. So you are adding HCl and then AgNO3. Okay. And then if you have to test for you can say halides, you need to add HNO3. Okay, because when you're adding HCl, it dissociates into H positive and Cl, and that is chloride line is coming. And this test is actually nitric acid plus you can say silver nitrate, and that basically if there is chlorine, bromine, or iodine or halides that are present, then you can easily detect what sort of halide is there. Okay, so reason is that is because HCl gives Cl negative ions. Okay, the test should be using HNO3 to ensure presence of halide ions, that is chlorine, bromine, and iodine. Okay, that is how it should be coming, because when you are looking for a salt and you are looking for a certain ion, because silver, from what will happen here is that silver chloride or white precipitate of silver chloride may form, and white precipitate of silver chloride actually was or chlorine was not present in the or we can say that chlorine may or may not be present in the solution W. Since you have added hydrochloric acid, that can be a source of chlorine, and that is or that may be leading to the silver chloride precipitate, or that is white in color. So to ensure that, we need to have nitric acid or HNO3 with aqueous silver nitrate to ensure that we have no chlorides added into the solution. So chlorides, bromide, iodide, or halides added into the solution. So if the solution contains a halide salt, it will make a silver chloride or silver bromide, silver iodide precipitate, and those precipitates will be giving different colors, and we can easily identify the halide based on the color. But since we have added silver hydrochloric acid, we are actually giving it a halide from ourselves. So that is not, that may or may not be present in the solution W. So that is why the test will not give us the actual value. State, how does the test and observation show that W does not contain sodium ions? So sodium ion, remember sodium ion flame test should give a yellow flame. So the flame test is no color. So the flame test is giving no color. For sodium, it should be yellow. Okay. Then it says identify the cation and anion in W. So cation, we have already determined it's ammonia, NH4 positive, or and anion is actually the sulfate test we have done here. This is the SO4 negative. Okay. So good choice would be to go for sulfate. Okay. So sulfate ion is there. Okay. So then part B says student adds dilute hydrochloric acid to copper carbonate. The gas and a solution are produced. So HCl, copper, carbonate. So the gas, it would be, you can say copper chloride plus CO2, okay, plus H2 gas maybe. So what will happen? So so a gas is produced, so carbon dioxide is coming out. So H2. So carbon dioxide is coming out. So carbon dioxide is coming out. So it means that effervescence occurs. The gas turns lime water milky. Okay. Describe how to do flame test to confirm the presence of copper 2 anions in the solution. Describe how to do flame test. So take a glass rod to take a small sample of salt on its tip. Move the tip to a burner flame. Observe the change in color of the plane. For copper 2 ions, we'll observe bluish green color is observed for copper 2 ions. Okay. Then moving on, it says describe one other method the student could use to confirm the solution contains copper ions, copper 2 ions. Okay. So again, follow the, you can say, sheet that is given at the end of your answer booklet. There are two methods. Number one, write any one of them. Number one method is add aqueous sodium hydroxide to the solution in a test tube. Blue precipitate of, or you can say blue precipitate is formed. Precipitate insoluble in excess of sodium hydroxide. Okay, part two, we say add aqueous ammonia to the solution in a test tube. Okay, again a blue precipitate is formed. Precipitate is formed. The precipitate dissolves in excess UH, giving a blue solution. Okay, you can write any one of these two tests and you'll be getting complete credit for it. Okay, so moving ahead, question number 4, the last part, it says baking powder is used to make cakes rise when water is added to baking powder, carbon dioxide gas is released. Okay, the longer baking powder is stored, less carbon dioxide is released when water is added. Plan an investigation to show which two different samples of baking powder has been stored for longer. Your plan should include use of common laboratory apparatus, the two samples of baking powder and water. No other chemicals should be used. Your plan should include apparatus needed, the method to use, the measurements to take, the variables to control, how to use the results to determine which sample has been stored longer. You may draw a diagram to help you answer the question. Okay. So let's see. So we have given basically baking powder. Remember in the other version of the exam, it's the same question. They're just simply saying baking soda. And instead of the cakes, they're talking about bread, that it actually means the same. Okay. So we have to basically, so you have to draw a diagram in the answer. So just basically, let's try to answer it. So we will take two samples. So take two samples of baking powder, label then A and B. Okay. The samples should have same weight. Okay. Should have equal weight, rather. It's a good technical term, same weight. So you can say you can have a digital space. So the screen. So you can have sample A, sample B, call it as mass of A, call it as mass of B. Okay, so mass of weight. So same way, use a digital balance to measure the samples. Okay, so we need a digital balance for it. Now, place the, okay, it's instead of this, place, that's fine. Place the samples in two different conical flasks. Measure the weight of each flask before and after adding the samples. Record the values. So we have also made as in the container. Now what we have to do, so say this is our flask. We'll attach a syringe to it. Okay. And say this is our sample in it, and we will heat it over a Bunsen flame. We'll heat this flask over a Bunsen flame. So attach, what we're doing here is attach a syringe, attach a syringe to the flask and heat the sample for X minutes. Full stop. Record. I can call it as measure and record. Attach a gas syringe. You can call it a gas syringe, measure and record the initial and final values of the gas syringe. Calculate the value of the volume of the volume of gas used. Okay. Now repeat the same experiment with the other sample. Okay, now, so once you repeat the sample, then the sample producing more volume of gas will be the one stored for less amount of time. Okay, so that is or that one will be, or the sample of baking powder that will be was stored for less amount of time. Okay, so this is how you can write an